Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have seen in the previous two lecture was general queuing models. Now what we see next is what are called as queues with vacations. And what is this? This is not in any way a special case of GG1 models, but it is more we are going to look at the Markov or semi-Markov setup only. Okay. Since this is also queues with vacation is also a broad class of models which, like the impatience behavior or like the retrial behavior, is also a very important class, but we will use both MM1 and MG1 together when we want to analyze this. We are not going to look at in the GG1 setup. So in that way this is more of falls into the category of semi-Markovian queues, one can say. Okay. But what is this queues with vacations? Okay. This vacation is a very generic word which we use in queuing theory to denote different kind of things. It could be really, a server could be failure, or it requires some setup time, or it's really like for some reason or other, whenever the server is unavailable to the customers over certain duration due to maintenance, failure, setting up of the server, or whatever be the reason, those periods are what is we call it as vacations in generic term. Okay. So the specifically the periods for which the server is unavailable due to whatever reason it may be, they are all called server vacation periods. Okay. And as you would expect, for many situations, like this is a usual occurrence that you would find. For example, if you are going through a traffic junction, if there is no traffic regulator or traffic police there, of course there is no traffic light, suppose. If there is not there, then that's you can think of it as if that is unavailability of the server there. The server there is the traffic police who is regulating the traffic in that particular junction. So that's also a vacation, right? So like this you can find this notion of generic term vacation in many production system, communication system, computer systems, and one of the most fertile ground for such models is your wireless network that you have, various studies that one do which all involves this kind of vacations. Okay. Or nowadays, like in this era of energy efficient mechanisms being put in networks, right. So if for example, in military applications and elsewhere, where you deploy certain devices and to preserve power, it will switch off or it will work at a very minimal energy consumption rate, it will work. So those kind of things when you want to model, you really basically, if it switches off it becomes vacation, and if it is work at a reduced power, okay, then it is a variation of this vacation which is called working vacation, and like that one can model it in situations. Okay. So for example, here we are just given two simple examples which normally you would find. For example, machines producing certain items may need some periodic checking and maintenance. Okay. So at those points there may be customers who need to be served, but the machine, due to its maintenance activity, is unavailable to produce anything or to attend to the requirement of service requirement from the customers. So, the periods of random lengths of preventive maintenance, this is what is called as the period of server vacation. Server is unavailable here. Similarly, in a computer and communication system, besides being engaged in primary functions such as receiving, processing or transmitting data either in a system or over a network, if it has to undertake secondary work such as preventive maintenance or has to scan for new work or anything other than that, if you do, right. So, this is all will fall under the broad framework of vacations, and Tian and Zhang is one of the recent book rather monograph which gives lots of ideas about this. So, this is the title itself called Vacation Queuing Models, Theory and Applications. Another good reference is basically the little earlier one, which is Takagi 1991, is what then one can refer to for various kinds of vacation queuing models, where it arises and what are their applications and so on. Okay. So, that is what we are going to consider. Now, there are many variations of queues with vacations. Now, when it happens, each time when a busy period ends and the systems becomes empty, the server starts vacation for a random amount of time duration. Okay, so that is what you normally consider as vacation. Mean there is no more customer to serve. At that point of time, the server decides to take a vacation, right. Now, when he returns from vacation and if he finds one or more customers are waiting, then he comes back to the normal mode and he starts serving the customers until the system becomes empty again. This is called as an exhaustive service discipline, right. While the server is working, the queue behaves like a normal queue, right. Only when he is the server is on vacation, when the customer arrives to an empty system, service will not start because server is in some sleeping mode. Okay, you can think of vacation or in sleeping mode or in downtime, right. It is not in up condition, it is in down condition for whatever reason, that is what it is, right. But once he finds on his return from vacation one or more customers, he will start serving the customers, then it becomes like a normal queue, and if that service continues until it becomes empty, then that is what is called exhaustive service discipline. If on return from a vacation, right, because normal period is what now we will refer to as busy period, the server finds no customer waiting, then he waits for the arrival of a customer. Okay. This is called a single vacation system, means he will go for only one vacation and he will come back. On his return, if he finds that there is at least one customer waiting, then he will switch to serving the customer. If not, he will wait for the customer to arrival, much like the normal queue. So, this is a single vacation system, okay, which is denoted by V suffix S to denote the single vacation case. On the other hand, when he returns back from vacation, if he finds that no customer is waiting, then he will go for another vacation. Okay. Again, on his return, if he finds at least one customer, he will start serving. If it is not, then he will go for another vacation. So, he will keep on taking vacation until on his return he finds at least one customer waiting whenever on his return from a vacation, on any return, right. So, this is called as multiple vacation system and we denote it by VM, V suffix M, we denote it as multiple vacation, and Vs is single, the S is single, M is multiple, is what the notation that we will use it, just to refer to this. Okay. So, there are two scenarios that you could have multiple vacation and single vacation. Now, there are many other models possible. For example, the server goes on vacation, okay, and once he becomes empty, and then he comes back, he sees that some one customer, two customer is waiting, he does not start service, he goes for another vacation, or he will wait, whichever way it is, multiple or single vacation period, but he will not start the service until there are n number of customers are waiting in this case. This is referred to as n policy. Like this, one could have different variations, and there are plenty of them, okay. Depending upon the requirement at need, you can explore it further, okay. Now, vacations with exhaustive service is what we will be considering, meaning that whatever we have mentioned here, that once he starts serving the customers, he will serve until the systems become empty. That is what is the case, and in that case, if Vn in single vacation, it is just single random variable, because after a duration of a random amount of time, he will come back to normal period, which is, and then he will wait for the customer, or he will start serving depending upon whether the there was no customer or there were at least one customer waiting in the case. Now, in case of multiple vacation, we can denote the nth vacation by the random variable Vn, and we will assume that this Vn's are a sequence of IID random variable, which is independent of the service time, and the sequence Vn of the random variables may be independent of the arrival period, or it may be dependent on the arrival process. It may be dependent or independent of the arrival process, but we will always assume that this is independent of the service process. Okay. Let us call this Fv to be the CDF of this random variable Vn, and Fv star is the Laplace Steele-J transform of this random variable. Now, if you consider a standard GG1Q with inter-arrival time as A, with its mean as 1 by lambda and variance as sigma A square, and the service time S with a mean of 1 by mu and the variance of sigma B square, then we shall denote a Q with general inter-arrival and service times and with single vacation by this notation, GG1 with an hyphen Vs. These are all not standard notations, but we will use this, okay. And the corresponding Q with multiple vacation by GG1. You do not need this GI because we are not really using this GI, so you can remove this. So, it is a GG1 Vm. And also one more thing that you can notice, the inter-arrival time here we are calling it is by A, so which was equal to T in the case of GG1, that we have used it here, okay. So, this is you can remember that, okay, that is what it is A here, does it matter, it just we are defining what it is in the particular context, okay. And the corresponding multiple vacation case is what we call it as GG1 hyphen Vm. Here we consider only vacation queues with exhaustive service, okay. But then as against this exhaustive service discipline, there could be situations which gives rise to a different varieties of non-exhaustive service discipline, okay, under which the server vacation may start even when some customers are present in the system, okay, right, or he will not start service and so on. So, that means two cases, again there is a preemptive and non-preemptive one can introduce, where vacations may preempt an ongoing service, for example, in the case of breakdown of the service mechanism, right. When service is going on for certain customer, suddenly the server breaks down. Non-preemptive case may, in this case what, where the vacations may commence only at epochs of service completion or vacation termination, in the case of a scheduled maintenance, right. So, when the vacation starts, whether it preempts any ongoing service or without any preempting the ongoing service, because the server can take vacation while there are customers waiting, meaning that when there is even when the service is going on, he can take vacation. So, whether that vacation is a preemptive one or non-preemptive one, meaning that whether it is preempting the ongoing service of the customer or not is the question here, okay. If it is a scheduled maintenance, obviously you would wait, right, for a service completion to happen, right, But if it is a failure, sudden failure, then you will not be able to control whether what will happen to the current service. So, you could have these two cases. There are very different kind of specific non-exhaustive service such as gated service. What is that? Which is also prevalent in communication network or computer network areas. Server takes a vacation, he comes back from vacation. What he will do is that he will close the gate at that point of time, and whatever the number of customers who are available at that point of time when the server returns from vacation, he will serve only that many customers before he takes another vacation. This is called gated service. You just put a gate and then you serve these customers and then leave. And different kinds of limited service, right? I can assume that a server takes a vacation after serving say one customer, right? Maybe like it is some kind of refueling or something is required. Now after serving one customer, you will take a vacation. So to replenish or refill whatever item that is required before you start serving the other customer. So that's a kind of a limited service, decrementing service, right? Once he comes back, it will be at the full capacity and then it might be lower or whatever is the case. There could be different variations that one can think in these cases, even within the non-exhaustive service cases, which are all of them are important from their own perspective, from their own applications point of view. Okay. There are even beyond this exhaustive, non-exhaustive, even with the exhaustive, then you could have other, like now recent phenomena is whatever which is mentioned as working vacation queue. One important property that you would observe when you are dealing with such vacation queues is what a specific stochastic decomposition property. Okay. So, this is for the vacation queues, this is an important property, stochastic decomposition, because you always look for such kind of decomposition in such models. And what is that? Under certain conditions on this vacation sequence, Vn is what? The vacation duration periods, both for the single vacation or multiple vacation models, the steady state waiting time is the sum of two independent random variables. The steady state waiting time can be written as a sum of two independent random variables. One is the waiting time in the same GG1 queue but without vacation, and the other is a random variable that is related to this vacation sequence, vacation duration sequence. Okay. So, this is what is the decomposition. So, the steady state waiting time is a sum of two random variables. One is the usual GG1 model without vacation. The other quantity is then the quantity that is related to the vacation sequence. Now, like when this has this, then one need not worry about only this second part alone you need to worry, because the first part comes from the analysis of the corresponding model but without vacation. Whatever be, whether it is MM1, MG1, GM1, whichever model you take it, or GG1 in general we will say, the corresponding model without vacation plus this, the quantity that is related to the vacation duration. Now, if the queues are having Poisson input, then such a decomposition property holds for the queue length distribution as well, not just for the waiting time. Waiting time it holds in that generality GG1, but for queue length, right, but for queue length it is you need Poisson input case. In that case, even for queue length also you have this decomposition property, that one is it can be written as the sum of two random variables, independent random variables. One is the queue length of the corresponding model but without vacation, the other one is connected to the vacation sequence. Okay. So, because of this kind of stuff that we want us to say, like we are studying this actually after our GG1 model, though the models that we consider will not consider under GG1 case. Okay. Fine. So, this is an important property you always look for in any vacation queuing model, such as stochastic decomposition property. Okay. Now, let us consider as the first model an MM1 queue with vacations, right. So, this is we could have done along with the Markovian queue, but we are doing it for the reasons which we have already said. Okay. What we have now scenario, you have a usual MM1 queuing system with usual notation and the stability condition rho, which is lambda by mu less than 1. In addition, what we have, the server vacation is what we are introducing. The server goes on vacation for an exponentially distributed duration with rate lambda, with rate theta. Now, this happens as soon as and only when the queue becomes empty. So, that means in the exhaustive case. We already said that we are looking at only the exhaustive service discipline case is what we are considering. So, the server goes on vacation for an exponential duration with rate theta as soon as and only when the queue becomes empty, which is the exhaustive case. Now, on return from vacation, the server will go for another vacation or possibly more vacation if required, if the system was empty on return from a vacation. That means that what? We have a multiple vacations case. So, this is basically MM1-VM model. So, basically we have here MM1 VM is the model that we have here, right, in that notation that we have just introduced here. Okay. Now, this is what the model that we are considering. Now, as you see, this model can also be thought about as a model connected with setup in a machine production system context. Okay. So, that is what we are saying. This multiple vacation MM1 model can also be thought about as an MM1 model with a setup time, that is a machine with setup. How? As soon as the server becomes free or the machine becomes free of any customer, in this case jobs, then the machine is switched off. That is what we call the server is deactivated as soon as the queue becomes empty. Now, when the new customer arrives at an empty system, now a setup process is need to be initiated, which starts the server, and it takes an exponential amount of time with rate theta is what. So, this model is exactly same as the model for this situation. Now, this is where this N policy business might come here, because you do not want to start as soon as one customer comes, right. You want to wait because there is a setup cost and setup duration and so on. So, you would want to wait till certain number of customers accumulate and then start the machine. That is a normal thing to do in such situations. So, that is what this situation is. So, N policy is just extension in this context, one can make it. But here, as soon as the one customer comes, the setting up of server starts and it takes an exponential amount of time with parameter theta, and after that the server starts serving the customer again. This is same as an MM1 working multiple vacation concept, right. This model is what is here. Okay. Now, we will assume that inter-arrival times, service times, vacation times or setup times, whichever it is, they are all mutually independent. So, usual MM1, we have introduced a multiple vacation idea here. That is what we have here, right. Now, this model can be represented as a continuous time Markov chain, as you know by now, where the state of the system at time t is characterized by this two-dimensional quantity ij and j of t, where I and j denote the number of customers in the system and j denotes the state of the server. 0 means server is in vacation, 1 means the server is in busy period, meaning it is in working condition or normal period. Okay. Now, it is clear that the state space of the two-dimensional CTMC is there is a 0, which we still retain it as 0 0 for reason which we will say later. So, there is a empty system along with I and j, where I is there is at least one customer and the system state is 0 and 1 depending upon whether server is in vacation or in busy period, where I0 indicates, as we just said, the server is in vacation period and there are I customers in the system. I1, server is in busy period or the normal period and there are I customers in there, and Pij denote the steady state probability of the system being in state Ij is what this steady state probability is. Now, let us look at how we can model this by a CTMC and what are the state transition diagrams, right. When the system is empty, right, the server is in vacation, right, arrival can happen to make the system becomes 1 0, right. Now from 1 0 again arrival can happen to make this system to move to 2 0 and so on. Any number of arrivals can happen with rate lambda. So, the system may move along this line. Okay. Now, if it is in 0 0 meaning server is on vacation, when he comes back and sees that system is in 0, he goes for another vacation. So, he continues on vacation, right. So, in this particular case, when the system is in 0, vacation never ends, right. When there is at least one customer, when the vacation ends, that means with rate theta, right, the system, on an arrival from vacation, if you find the system is at least one, then the vacation will end and the system will move to the busy period or the normal period. So, that means the server will become now the j, the second quantity will become 1 with the corresponding customer remaining as 1. So, with rate theta, this will move from 1 0 to 1 1 and same thing will happen with 2 0 to 2 1 or n 0 to n 1, right. It is here and then you will see that this vacation ends here, then it will move to n 1 and then server starts the normal period, which means he starts serving the customer again. Okay. Now, while customer is getting served, for example, if there is 1 1, which means there is one customer, the server is serving the customer. Now, there could be an arrival to make it to 2 1 or there could be a service completion with rate mu and then it will then boils down to 0 0, then the server will go on vacation, then the other process will start. Now, if it goes to 2 1, right, then if there is a service completion, it will go to 1 1 or if there is an arrival, it will go to 3 1. Right, it will go along this line, this upper line when you have server is in the normal period with arrivals and departures happening in the usual way like an MM1, right. So, this 0 if I plug it here, this there is one lambda and mu tag if I take and if I remove all these things, then what is you are going to get is a normal MM1. Now, you have segregated this particular state. So, both of this probabilities represents the number in the system being the same, right. Whether this is basically this n1 and n0, the sum of these two would represent the number in the system being n, right. That is what we have done here in this case. So, this is what is the state transition diagram in the case of MM1Q with multiple vacations. Okay. Now, if I write the stochastic flow balance equation for this particular state, I will have 1 which is this quantity, right, lambda p00 equals mu p11 and for p11 you will have lambda plus mu p11, right, and theta p10 and mu p21 is what then you will get here, right. So, this is what you have for p11. Now, for pi0 from 1 to this, you will all have this equation because this will be lambda plus theta times pi0, right, and you will have this lambda times pi minus 1 0. This is what you will have for I0 and for I1, suppose if I take here, right, it is lambda plus mu times I1, lambda times I minus 1 1, mu times I plus 1 1 and theta times I0 is what then you will get these three terms. So, this is what is the steady state balance equations. Now, you can solve this. Okay. Again it is 2 dimensional, solving will be little difficult, but it is solvable. One can obtain this like what we have done for retrial Q and so on. In a similar fashion one can do this. Okay. But what we will try to do is that we will try to solve this balance equation by this method, what is called as matrix geometric method. It is just to illustrate how this method works in the generic problem and why this is so powerful tool to solve such processes. Okay. We will try to get the essence of this approach through applying this two. We could have applied this to say for example in our retrial model case and elsewhere too, but we will try to here. Okay. Now, to apply this, of course, it's basically the QBD model and so on, what one calls it. You see that suppose if I call this as level, this whole thing, this n denotes the level, whatever be the number of states here. So, this is what we call it level. Then you see that from n1, from the level n, the transitions happen to n minus 1 or n plus 1, no matter whether it is n0 or n1 in both the states. Okay. So, that is what makes our life easier, right, that is what we are observing. So, that makes it that the last two equations for I greater than or equal to 2, if I combine, right, if I consider this Pi0 and Pi1, that corresponds to, this is a vector Pi now, but this vector Pi is correspond to number in the system being I, right, but this is a vector, this Pi is not a scalar quantity, it is a vector quantity, you should remember. Now, by combining these two equations, which meaning the combining the equation corresponding to these two, you can write this in this form, okay, where just that you are just combining these two equations, you just write it for I0, I1, right, in the matrix form, two equations you will have for I greater than or equal to 2, I greater than or equal to 2, you take from these two sets and then write down, this is what you will get here, where my A0 is this, A1 is this and A2 is this, right, because from I plus 1, A2 and I is connected with A1, I minus 1 is A0 is what then you will get here. That means this is corresponding to the arrival part, this is corresponding to the service completion part, this is corresponding to the movement bit within the level, right, within the level. This is to the lower level, this is to the higher level is what then these things will come here, because this matrix equation is what you will get. So, this is the vector matrix equation in this case, right. In matrix geometric method, any such equation is what you are trying to get, you are trying to put it in such a form where now you can look at the similarity of this equation with an MM1 system, right. In MM1 system, assume that suppose if this were scalars, you had Pi minus 1 and Pi and Pi plus 1 is what was related, but in a scalar fashion, but here in the vector fashion or matrix notation, right, with the coefficient of matrix and these as vectors, this relationship is true. This is what is the similarity that you make use of it when you try to use this matrix geometric method. Geometric method or geometric probability distribution is what you would obtain in MM1 case. So, this is matrix version of that is what you are looking at here in a way. So, this is what is the equation. Now, we will first simplify this vector matrix equation by eliminating say Pi plus 1 from here. How do we do? By equating the flow from level I to level I plus 1 and the flow from level I plus 1 to I with the flow balance, what one can observe is that this is what one can observe. Pi0 or Pi1 times lambda would be equal to Pi plus 1 times mu is what then you will get, okay, by equating the flow between these two cases, okay. I to I plus 1 and I plus 1 to I is what then you are equating, then you will get this equation. This one, right, Pi0 Pi1 is what we are, if you put it in a vector form, then this is what you call Pi. So, using that I can write this as Pi times A3 left hand side, the right side is Pi plus 1 A2, because this is what is the term that you would be having here, where A3 is 0 0 lambda lambda is the matrix. So, what you have observed is that this quantity, which is basically comes from this factor, right, that is basically this factor, this gives you rise this, and this one is equal to Pi of A3, where A3 is this quantity. Now, if I substitute that in place of Pi plus 1 A2, this Pi A3, then I will get Pi minus 1 A0 plus Pi times A1 plus A3 equal to 0 for I greater than or equal to 2, or you can write Pi as minus times Pi minus 1 times A0 into A1 plus A3 inverse, or you can say something like Pi minus 1 times some R, some matrix R, where R is exactly this matrix, which is turning out to be in this particular case is the matrix given by this expression, because one can compute what is A1, A3, A0, everything you can compute this R, this is what it is. Okay. Now, what you are having Pi is Pi minus 1 times R, which is equal to pi minus 2 times r square, because pi minus 1 again I can write it in the same way as pi minus 2 times r. So, in total it is pi minus 1 times r square for pi. So, in general if you iterate it will lead to pi equal to some p1 times r to the power I minus 1 for all I greater than or equal to 1. Now, you can make a similarity with MM1. MM1 also you had some p0 times rho to the power r or rho to the power I is what you got it as for pi. So, it is in matrix geometry the main point or the main crux, the essence is that to get this matrix R such that this kind of expression, remember this pi, p1 they are all vectors, right. So, in when this vectors but corresponding to the same level, right. So, this vector in vector form, this will resemble a geometric kind of form is what then you look for in matrix geometry case. Now, once I have this one, all pi's are expressed in terms of p1. Now, you still have these two equations only we use, that too from I is greater than or equal to 2. So, now you have one equation here, one and another one. So, there are 3 equations here and the normalization conditions. All of this can be used to determine this p00 and p1 has now 2 elements, right. So, these 3 equations along with that normalization condition, which means one of the equation you can throw, use the normalization condition to determine these 3 quantities you can do. Okay. So, the normalization condition now if I write it, it is basically sum of pij where I and j, which is basically p00 plus whatever is the p1 terms, which will sum to be equal to this quantity is what you would observe here. So, this is what is equal to 1. So, this is the normalization condition that you would obtain, and where E is as usual the column vector of 1s. So, this is what is the normalization condition, you will use it. Okay. Now, once you get this, then you can obtain L, which is basically I times pi times pi is a vector here, E is vector of 1, which means basically you are summing these 2 elements, multiplying by I is what will give you the number, which is basically it is equal to this quantity, because pi you know it is p1 times r to the power I minus 1, which is basically turning out to be this quantity. Now, I minus r to the power minus 2 are the inverse, you are squaring it, multiplying by this vector and multiply by this vector is what you will get this L, and from Mitchell's law you will obtain W to be equal to L by lambda. Okay. This is what is the essence of metric geometry. In this way you can solve this system. Directly also after a lengthy process you can also solve, there is no problem with that. You can use operator method or generative function method, you will be able to solve this model as well. Now, this is after obtaining this, but from the mean value arguments and using Pasta property and Little's law, we can obtain W directly as this. Just to exhibit certain things, we just wrote this. What is that? You look at the waiting time in the system is basically the waiting time in the system, right, in a normal MM1Q plus the waiting time which is connected with the vacation random variables. So, it turns out that in this particular case that the extra delay that you have in this MM1 with vacation model is basically the extra delay is again an exponential distribution with parameter theta. We just said stochastic decomposition, that is the normal without vacation plus the extra one which is connected with the vacation, and in this particular case it turns out that it is exactly the way. So, expectation is simply sum of these 2 quantities. So, that is what is the case, but even the distribution itself will turn out to be exponential only in this particular case. Okay. So, this is what is the MM1 model with multiple vacations. Now, this model can be analyzed with single vacation as well. So, what one has to do, you have to make a slight change to the model setup. The server after returning from a single vacation either starts service if the system is non-empty at the point of time, or waits for a customer to arrive like in the normal queue. So, what one has to do is that one more state, for example, here what would happen here, right. Now, here there is no point in multiple vacation case, vacation will not end while the system is empty, because whenever on return from a vacation if the server finds the system empty, he will take another vacation, right. But in the case of single vacation case, like he he will end his vacation and he will bring down to the normal mode. So, there will be another state, right, 0 1 is what then you would introduce here, and there will be a movement theta here, and from here there is a lambda here, it will come here. These are the only two extra links that you need to add to this diagram to get a model which is an MM1 with single vacation, and one can also analyze along similar vacation. And that is the reason why we did not call this as simply as 0. 0 0 we kept it, because in single vacation case we could have add another state which is 0 1. In that case vacation will end while the system is in empty and the arrival can happen. That is only two links that you need to establish, which means that there will be a curve here and then there is an arrival. So, this is what would be the structure that you will have with appropriate rates. Then you will get a system of equations, and then you will try to solve for the case of this MM1Q with single vacation. It is a similar way. So, one need not do that is what the. So, this is what we do for the MM1 with vacations in this particular case. So, what we have seen is a how does the vacation comes, and when in this vacation is introduced in a simple MM1 model, how one can analyze. And we have also given the essence of what is a matrix geometric approach one can adopt to solve such problems when you have this kind of multi-dimensional situations, when clubbing basically you are condensing one dimension to make it look like a single dimension, but now not in a scalar terms but in vector terms. That is what will gives rise to applicability of matrix geometry, which is a very powerful tool, which the essence you can see it from this analysis. Okay. So, we will stop here, we will continue in the next lecture. Thank you. Bye.